Okay, here's another problem for you to work. We have an organic substrate, reagents, conditions on the reaction arrow. I'm going to give you a chance to hit pause, go away, figure out what the product is, and tell me what the mechanism is. So again, E1, SN1, E2, SN2, and the product. So hit pause and do that. Okay, you're back. Do you have a leaving group? Yes. On a tertiary carbon. All right. Iodide is a leaving group. It's on a tertiary carbon. Beta hydrogens? Yes. We have beta hydrogens here. Beta hydrogens here. So elimination is possible. I should say, we have a leaving group on a tertiary carbon. Should have said this. No SN2. We're not going to be able to do SN2 at all. If you have a leaving group on a tertiary carbon, you can't do SN2. Strong base. We don't have a strong base. So iodide's not a base. Methyl ether here is not a strong base. Ethanol is not a strong base. Ethanol is a solvent. Some of you have drunk it. You've all probably seen it. It's not caustic. You can soak your hands in it. Ethanol is not a strong base. Again, the oxygen-carbon bond is covalent. The oxygen-hydrogen bond is covalent. That's all covalent. So this is that. There are no charges there. There's no negative charge on oxygen. That's just ethanol. It's a weak base. It's a poor nucleophile. So no. Do you have a good nucleophile? As I've just said, no. Taken together, this means no SN2 or E2. So you're down to SN1 and E1. And you can do SN1 with a tertiary iodide. As a matter of fact, if the iodide leaves, let's get rid of some of this stuff here. If the iodide leaves, so if the iodide leaves, we get a tertiary carbocation, right? Carbon, carbon, carbon around it. It's conjugated to the benzene ring, so it's a benzylic carbocation, so it's quite stable. And then the nucleophile, so or base, ethanol can either come in and attack the carbocation, or it can grab a beta hydrogen. And now the question is, which is it going to do? And the thing that will direct you is the temperature here. So low temperature tends to favor substitution. But you should be aware that when you're differentiating SN1 and E1, there's probably always a little bit of elimination that happens. But in the substitution, ethanol attacks the carbocation. I'm going to get rid of this writing up above. So that's the initial product. So ethanol attacks the carbocation, nucleophilic oxygen, the weakly nucleophilic neutral oxygen attacks the carbocation. It's going to give you a positive hydrogen or a positive oxygen here, bonded to the tertiary carbon. And then either iodide or another molecule of ethanol can come take that proton, neutralize the charge on that oxygen, and the product will be that'll be the major product of this reaction. Nucleophilic substitution, unimolecular, so the rate's only dependent on this iodide. And this carbon, that carbon is chiral. It's chiral here. I've shown it in only one stereochemistry here, so this would be what? Ethyl's probably the low priority. No, yeah. So iodide, 1, 2, 3. That's going to be an S-chiral center. Here, though, this will be racemic because it goes via this carbocation, which is planar and achiral. Okay, so that's your product. It's an SN1 reaction. If you said E1, you're probably not all that far off. you're going to get a tri-substituted alkene that is conjugated to a benzene ring. It's going to be a really stable alkene. So E1 is going to be a problem, or is going to be a likely minor product in this reaction as well.